Welcome back, everyone, to IEEE 2021. We have our next lecture online on both platforms. Up to now, we have covered feature extraction, classification, geosemantic information derivation, object detection, and change detection with deep learning for remote sensing. The current lecture is titled Prior Knowledge in Deep Models for Remote Sensing. This will be presented by Devis Tuia. Devis Tuia is currently in EPFL, Switzerland, where he leads the Environmental Computational Science and Earth Observation Laboratory. And without further ado, I'll leave the stage to Devis Tuia. Thank you once again for being here and for presenting your lecture.
Thank you very much, Alp. Thank you, Gülsen and Mustafa and everyone to be here. It's very nice to be back at IEEE after a few years. We were all together in Istanbul. This time it's online, but okay, we make it happen, right? Yeah. And yeah, so I'll be your host for the next 1.5 hours. And yeah, I thought it would be nice to talk about prior knowledge in deep models and to give you a bit of an overview of what's going on in the community, and give you some examples from recent publication. So let me share my screen so we can. Okay, can you confirm me that you see everything okay?
Yes.
Yes, fantastic. So yeah, so the topic today is prior knowledge, and basically, I mean, you have been learning a lot about deep learning classifier in the first part of the summer school, and I hope that you've got to the point where you see how all these methodologies can be very useful for you, and maybe it's a bit overwhelming, and you've seen all these models that are around, and they tend to work reasonably well, and you can tweak them the way you want. So I mean, the question I want to share with you today is basically to see if with a deep model we can basically solve remote sensing image processing, and if the story is finished. I mean, you can imagine the answer, otherwise I wouldn't be here talking to you. But okay, let's start from the beginning. So these are the kind of things we've been seeing so far. So there is some remote sensing image, that be satellite or aerial, and a first approach to how to solve that is to basically take a deep network that is maybe pre-trained on a large set of natural images, let's say ResNet, and train this guy with some annotations that you have, like the ones here on the right, and at the end get to some reasonable results. And this is something that it works. I mean, there are a lot of very successful examples about that. Also in other recent literature, it seems that if you take a unit and you train it reasonably, I mean, you end up at the top of the leaderboards, and basically have some results that look very promising. Okay, but I mean, my point of view is that all this is great. It works very good. But I mean, it implies also a number of things. So first of all, I mean, it implies that we have at our disposal a very big learning set. So labels, basically, that represent all the classes that we want in all the acquisition conditions that we want. And also, I mean, it forces us to stick into red, green, blue images. I mean, most of these pre-trained models you find on the internet accept 3-channel inputs. I mean, it's moving on from there more and more. But let's say if you just want to download a pre-trained architecture and use it on your data, you probably have either to use the RGB or to start playing some tricks to make them look like RGB. I don't know, making an image out of the NDVI, and you name it. Okay, but another thing that for me it's a bit of a pity is that we end up being completely tributary of pre-trained models coming from another field. And if you, like me, have been working in remote sensing for a while, well, there is a number of things that you know about remote sensing images that you can use. All this knowledge about the task, all the knowledge about the fact that we're dealing with space and geographical coordinates and so on. And all this, you can also decide to plug it into your model. And a second thing that it's maybe a little bit of a pity is that in a very large body of literature, we tend to go for what we know, which is pixel classification, while there are other tasks that are very relevant and that we can now approach with this new technology based on neural networks. So basically, the story today in this 1.5 hour will be to talk about prior knowledge, what it is, why it is important, then to see some methods that allow us to encode prior knowledge into deep models, and finally, hopefully, then it gives you some, envy to try it out, which is the final goal of all this. So we'll go on 3 levels that are characterized here by this funny little man that comes from a video game I deeply care about, Ni no Kuni. And in the first part, we talk about the why. So why encoding prior knowledge in deep learning is important. Then in the second part, we'll talk about one specific type of prior knowledge, which is spatial proximity through random field models. And in the third and last part, I'll show you a couple of examples where we can do other things than pixel classification and try to approach and hopefully solve other types of problems. I don't know if you can unmute. If you can, ask you questions or write them in the chat, and then if someone can just stop me and ask the question, I'm very happy to do it live, or we can leave it to the end if you prefer. I don't mind being interrupted. Let's put it that way. Okay, good. So let's start from the beginning. So why on earth we would like to encode prior knowledge in deep learning when we have deep learning that seems to do just fine? So try to see it like that. The thing that we are trying to solve is to train models based on neural network that we are able to train, okay? And as I told you before, we do not always have large labeled data set to train models completely end-to-end. So pretty often we need to rely to reduced size labeled set, and maybe maybe you just have one small GPU card to make our calculations, so we cannot really afford to train for 3 months just to have one study out and then maybe having a paper. So what we want is basically having small models, but that allow us to be as good as if we had a very large model that would not involve prior knowledge. So look at, for example, here at the image on the right, you have on the x-axis the size of the model expressed in number of learnable parameters, and on the y-axis here you have the test error. So you would like to be as low as possible on the error, and the thing that I hope we are able to achieve is to have something like the yellow or the violet curves, where with the small models, we can still reach very low error that are comparable to much larger models that will not encode prior knowledge explicitly. And since I'm showing you this figure, which refers to a very specific type of prior knowledge, I thought that to work on one specific one, which is rotation. And why rotation and not others is because one of the greatest selling points of convolutional neural networks were there were translational invariants across the image. So it means that your filter is actually a very small filter that slides all over the place instead of having one neuron connecting to every single pixel in the original image. And by using these smaller filters is basically what make the deep networks able to be trained on standard GPUs. So if we can do it for translation, can we do it for rotation? And this makes sense because, if you look at this image here that you see on the slide, this is usually the part when I ask people what do they see in the image, but you know, we are remote, so that's it. So you will see this red car here, but if we start rotating the image like this, I mean, it is still a red car. The fact of rotating the image doesn't impact the final prediction you need to do, or also in this case, we're still looking at this red car seen from above. So it seems kind of logical that a model should be able to ingest that and in some ways not to be too concerned about the arbitrary rotation of the image. But surprisingly, if you look at standard convolutional neural network, this is actually not true, because if you take one image like this image of the H here and you apply a convolutional filter, you know, this little guy that you slide it over the image, this is the type of filter that you get. Okay, you get some kind of directional gradient from left to right. But if you turn the input, so if you have the H now turned 90 degrees, well, and you apply the same filter, you see that your result is completely different. Your result is not just a rotated version of the filter obtained before the rotation. So by default, a CNN is not rotational invariant. And this is, for example, one thing that we tackled in the past with a model that at the end of the day would get you the same result in terms of activation map after rotation of the input. So it will be like the same activation, just rotated by 90 degrees. Okay, so how do we achieve that? Well, one thing you could do if you wouldn't care about the creation of the activation map would be like to do massive data augmentation. You could say, okay, I rotate my image in all the rotation I can imagine, and I just throw them in my CNN. And it doesn't matter if the filters are difficult. If my network is big enough, I can contain all this difference in the learnable parameters. And then every time one image is rotated a specific way, well, one specific filter will activate. Okay, this kind of works, but it forces you to like oversize your model, which, as I said before, is maybe something you don't want. So how can you make this rotational invariance happen at the level of the filters? So I have an example here, and I mean, it is as simple as it gets. You have an input image, let's say this wonderful image that shows you where I'm from, and you apply a convolutional filter. Let's say it's this one, and you get to an activation map, a kind of diagonal directional filter. The thing that we do is that we start rotating the filter itself. So we keep the same filter with the same parameters, and we just rotate it. And every time the activation map gets different. So we'll just apply the standard CNN, but instead of every time learning a different filter, we learn blocks of filters. So you see here, every colored block corresponds to one filter that we rotate. And this gives you a kind of a tensor of activation maps, each one corresponding to one specific rotation. So if we would have stopped here, we're just doing standard CNN, and we are basically constraining the filters to be similar in groups. But actually, we take a step forward because there is a lot of redundancy. So like you have to deal with huge tensors. This is a lot of information that you basically are flushing down the drain. So the thing we did was to apply what we called an orientation pooling, which basically means that we take for each pixel in the activation map tensor, we look at the different activation per different rotation. And we go for the maximum, like a max pooling will do. And in this case, you see, this is the maximal activation value. And we pass to the next layer this value, so the value of maximal activation, and the angle that generated. So in this case, it's 180 degrees. And to have these two information go together, we basically express it like a vector, where the angle of the vector corresponds to the rotation you're applying, and the length of the vector is basically by how much the activation was strong. And you see, so by applying this principle related to orientational pooling, our activation map starts to look very different. Instead of having one 2D image-like result from a convolution, we get what we call a vector field. And this vector field will tell us for each region of the image, which is the rotation that is mostly interesting to express, in this case, that is a pizza. Then we do spatial pooling as usual, and we basically pass it to the next layer. Okay, but as you see, the problem is that now the inputs we have are vectors and not images anymore. So, I mean, at the next layer, you will be obliged to have some kind of vectorial filter instead of an image filter. But that's something that can be solved okay, because if you think about a vector can be decomposed in two orthogonal components in the horizontal and vertical direction, which means that if you have this vector input times a vector filter, it basically is the same that taking the horizontal component times the horizontal component of the filter plus the vertical component times the vertical component of the filter. And the result we get is exactly and completely the same. Okay, so at the end of the day, it looks like that. So we have the image, the groups of filter, get the activation, pull the maxima, get the vector fields, and then we pass the vector field to the next, where we have vector filter and not image filters anymore. But with this decomposition, we still end up with some activation maps that look like images, and we can play the same trick again and again and again and again. So in other words, it's a way to encode rotational invariance by using all the ingredients that we know, which are convolutions, rotations, and sums. And with this, we are able to create a CNN that supposedly knows about rotation and should be learnable in a much, much smaller way. So if you want to give it a try, just to make some shameless advertisement, we have a couple of implementations. One on MathConvNet here and one on PyTorch. So I mean, if you want to play with that, all the code is open, and I invite you to have a look. So let's see how this works in practice. So basically, we could look to a series of problems like invariance, equivariance, or covariance. I just chose to show you one, which is the one maybe most close to pixel classification. And it's basically the equivariance, which means if you rotate the inputs by a certain degree, well, the final results must be the same, but rotated by the same degree. And this is something we want to achieve with this Rotational model. So to test this, I used a very traditional data set, which is the Vahingen data. It's a benchmark from the SPRS. Most probably you have heard about it in the other talks. And it's basically 16 auto-rectified images. We use 11 for training, 5 for test. They look like this chip here on the left. And each one of these images comes with a ground reference with some classes like buildings, streets in white, trees in green, and so on. Sorry, I poorly picked the images so that the image and the ground truth do not correspond. But you see where I'm going. Okay, so the model we use, it's what we call a hypercolumn. And it's a model that basically looks like a traditional image classification network, as you see here on the top. So you have the image, you apply some filters, get the activation, spatial pool, more filters, activation, activation, activation, activation. And then all the activations that are smaller versions than the original are upscaled with some, you just choose your favorite upscaling method. And then we stack everything together. So the original image and all these activation in a single tensor, and we learn a fully connected layer. So a multi-layer perceptron, if you want. And at the end, we get to the semantic levels. So it's a model that has been used quite a lot. I mean, there is paper by Maggiore, there is our paper with Diego Marcos, and I mean, it's a model that is fairly standard. But the difference here is that instead of using traditional filter, we use this rotational filter called RotaNet. And to show you a couple of results, well, we see that the RotaNet implementation compared with the standard CNN seems to do a decent job. So you see the prediction looks pretty good. It tends to predict more the cars than a traditional CNN, but this is more of a training issue. So I will not exaggerate about it. The story is that the prediction seems to be decently accurate on this data set. And the interesting part is that actually we have an accuracy figure that is, in the order of the 87%, which is very close to, like off the shelf, like CNNs. But at the same time, we achieve this same performance with a fraction of the parameters. We are talking 2 orders of magnitude smaller networks. So it's 100,000 parameters instead of 10 million. So this creates a model that is based on standard components, and you can train on your own machine because the number of parameters involved is much, much smaller. And this is basically achieved simply by encoding something that we know about the image, which is rotational invariance. So that's why I think it's a kind of cool development. And I mean, it doesn't bring you to like extreme new heights of performance, but it allows these models to be trainable on like normal resources that we could afford. Okay, so this is what I wanted to tell you about why we need prior knowledge. I hope you are convinced that using it it makes sense. And as promised, in the second part, we'll talk about one specific type of prior knowledge, which is spatial proximity. And spatial proximity is a good old favorite of remote sensing because, of course, like images are spatial, so pixel being in space, they are neighbor to each other, and we know that nearby pixel like to be of the same class, especially a very high resolution. And I mean, this is something that has been around for a while in the remote sensing community. If you are familiar with, I don't know, texture, math morphology, or all these type of techniques, it's always a way to include some kind of reasoning about spatial proximity at the level of the inputs, at the level of the image. Okay, and so the thing I want to discuss with you now is how we can look at this same problem from the opposite perspective. So, given a classification result that we can achieve with our favorite model, can we now take this prediction and try to make it more consistent with this vision of the world we have, that nearby pixels need to be of the same class, and without touching the input this time. So I don't want to like extract filters from the input before putting them in the CNN. I want to really work on the end product, on the final map. So yeah, as I told you a second ago, so there are all these levels that we can use to make a model understand spatial proximity. So number 1 and 2 are those that I was telling you about before. So pixels that are close by tend to have the same grayscale values. So if you take a spatial average, you will filter out noise and spatial details, or also the fact that objects are sharply separated. That means that if you are on a border of a building, what's on the other side of the building will probably have a very different gray value. And these two things are things that a traditional convolutional network is very good at, because they work on convolutions, so they learn all these filters that are contextual. So they will learn spatial averaging, they will learn edge detection and things like that if you train them well enough. The third way of looking at spatial proximity is, again, to look at the output. So you say if one pixel is classified as a building, its neighbor should also be classified as a building. And this is the one I want to deep dive a little bit in. So like in this example here, you see this image here of Los Angeles. If I zoom in this specific like edge of the roof and the tree that is just below, I mean, there will be a sharp boundary between the two, but at the same time, everything that belongs to the same object will be should be consistent. It's very unlikely there will be one isolated green, like classified as 3 pixel at 50 centimeter resolution, unless, I mean, okay, maybe sometimes with the resolution you have, you really can see something that small. But at the end, in your final map, you don't want to have have that information. If you're after building footprints, well, you want everything to be consistent. So we will use this as our prior information so that pixels that are nearby need to be more or less the same. So, okay, there is a number of solutions that have been proposed in the past. This is probably the simplest of them all. It's called the majority voting on the final map. And I mean, I imagine some of you could have used it. So you take the pixel here in the middle, you take all the prediction they have around them, and you take the majority. So in this case, you see, if you look at it as a single vector, with all the predictions, so red, red, red, yellow, yellow, green, green, green, green, well, the majority will be green. So you would like to change the prediction into the green class, because this is what the majority of your neighbors have said. And this will help you basically clean up all salt and pepper noise from your map, with respect to the size of the window you're using. So you can do it crisp, so take the final decisions and take the majority, or you can use posterior probability of classifiers. So, you have many classifiers that give you these probabilities. It can be a maximum likelihood or a random forest. To some extent, a CNN gives you something that looks like a probability, but it's not really. And, for each class, you will have a probability map that will tell you how probable that pixel belongs to a class. If you take the maximum, then you have your map. And you can use this information to be a little less harsh on how you filter by saying, okay, if the neighbors have been put in the tree class, but it's not very probable, I will maybe trust more neighbors of another class that is predicted with high confidence. And if you apply this principle to some real data, you see that when you use only your image bands with in this case, I think the classifier was a maximum likelihood, you see that the result is basically a lot of salt and pepper. So you see the tree has some grass pixels in it, and you have some parts that are not very sharp. You can partially solve it by computing a lot of filters. So you take some math morphology, you use everything together as an input and classify. So you already get quite a jump. You go from 73% to 81%. But if you apply this like local neighbor majority vote, you can still increase by 3 or 4%. And this is basically for free, because you have the map and you end up just taking a maximum, weighted or not, by the neighbors, and you get to a better result. Of course, since you do that in 2 steps, so the first step being classifying the image and the second being post-processing by the map, you cannot recover huge mistakes made in the original map, because you're still tributary of what was predicted in that specific original map. Okay, so this works pretty okay. But you're encoding a very simple prior, which is a pixel should have the same class as the majority of the neighbors. It's very difficult to encode other type of priors with this strategy of majority voting. The fact that rivers are lines, or that a commercial center is larger than a residential building. This is prior knowledge that requires a little bit more advanced type of encoding. You cannot just look at the direct neighbor of a pixel and get to a decision. And so the story is that there is a large literature about how to encode other type of prior knowledge using what we call graphical models. And one that I want to talk about with you is called a Markov or conditional random fields, that will basically give you a lot more freedom into how you encode your prior knowledge into the final map. So I don't know if you've heard about random fields models. If you have, you can take a nap for a few minutes. But I wanted just to show you the basic principle, which is basically it's changing a bit the chip from having, it's like what is the map that is the most correct in the sense of among all possible permutations of the map with all the classes you have, I want to really pick up the most probable, okay? And this can be based on a classifier, but it can also be based on a classifier plus some expression of our prior knowledge. And I mean, the finding this most probable map, I mean, if you had to do it by hand, by looking at all possible combination, it's quite an untractable problem because, I mean, look at the example here below. You have 9 pixels, 2 classes. So basically you will have 2 to the power of 9 combinations of different maps. So, I mean, if you have to look at them all in order to pick which one is the most likely, you probably, you know, will be here for a very, very long time. Okay, so, but at the end of the day, classifiers are here for us, and they're here to help us to solve this problem. So if you work with a classifier without any prior, so a random forest, a convolution neural net, I mean, the thing you're trying to solve is to find the final map, let's say Y, that maximizes the probability of being the right one, okay? And this probability, you can express this like the product of all the probabilities of every single pixel, okay? So what a classifier does is basically defines you this probability at each single location. And if you took the product of all this probability and you log it, you take the maximum of this and you will get the most probable map. Okay, by properties of logarithm, you can use a sum of the log of all these guys. And basically, this is what you do with your classifier. You go all over your data, you take them one by one, take the maximum of the probability, and at the end, you get to the maximal interesting one. Now, this is what classifiers do. But what they do is that they basically take your image, take every yellow circle here as 1 pixel in your image, they're all x's, and for each pixel, you will compute the maximal probability of the output. So every pixel is basically taken independently from the others. And that's not what you want if you know all these rules that nearby pixels should be on the same class. You're basically disregarding all this information. So now, how can we include this information in the story? Well, we can not only looking at each pixel one by one, which is the left part of the equation here, but we can also start to look at codependencies of pixels, okay? So we want to basically evaluate pixel location, the probability that the label of the central pixel is forest, while the label of the pixel on its left is building, okay? So xi and xj are 2 labels given to our pixels, and I is the central one, the one you are trying to classify, and j is one that is in its direct neighborhood. So I've called it ni here. And then you decide how big ni is, okay? You could look at for each pixel at all the others in the image, but this becomes super heavy computationally. So to make it feasible, you basically restrict your search space to neighborhoods around your pixel, because you can assume that if one pixel is a building at the center of the image, I mean, it's not really important what is the label assigned to a pixel 2 kilometers away. Okay, so as before, you have 2 products, we convert them into 2 sums, okay? We have one sum here on the single pixel label and a second sum here over the neighborhood of that same pixel. So the part on the left, same as before, you have your classifier, your CNN that you like, and the part on the right, it's where it actually starts to get interesting, because it is something that will tell you if the neighborhood is likely to be observed or not. Okay, but if I retake the image before, you remember before we had only the vertical line, so each pixel was considered independently. But now if we consider xi here, it means that this prediction will depend on the features of xy, but also on the prediction of all the other pixels this guy is connected with. So in this case, we are saying, okay, let's look at 3 by 3 neighborhood. So it means that you will also look at a spatial neighborhood in the output space this time. A very last detail is that we want to maximize the probability of the map being the good one, but this can go up and up and up and up. So it is actually better minimizing minus this same number, because then you can go towards 0. So, and this is basically the formula that you need to optimize in order to look at the same time at the pixel itself, given its feature, and on the spatial context of the predictions. So again, remember, the part on the left, you have it already. It comes from your classifier, your random forest, your SVM, you name it. The part on the right is up to you to design. And this is where it gets funny, because it's basically your job to encode the prior information that you want. And remember this, because we will see a lot of these equations in the rest of the talk. And every time try to understand what this V term looks like. So if you were after looking at direct neighbors, how likely they are, a good candidate would be to have a function that tells you if the two neighbors are of the same label. So it's a function that will tell you 0 if they're the same and 1 otherwise. And then you make 1 minus this guy. So that if the label is different, you will have a 0. And if the labels are the same, you will have a 1. So if they are different, you will penalize because your loss will not go down. And in the other case, it will decrease because you are consistent with what you expect in the spatial neighborhood. There are several solvers to solve this problem. So you don't have to figure out how to do it in practice yourself. I just named 3 of them here. The first one is probably the simplest, which is called conditional modes, which means that you go pixel by pixel, compute that equation for that pixel and see if you need to swap, and you keep going. You can go randomly, you can follow a list, and you iterate several times, and your map tends to converge with the optimum. And then you have other possibilities that are faster, but also more complex. If you want to look them up, the names are here, and you can go to the literature to see how exactly they function. What I want to do first is to drink some water. Is to show you one example of how we apply this principle on some remote sensing data. Otherwise, it stays too theoretical and maybe a bit boring. Okay, so the story of that work there, it's about fusing 2 words that sometimes don't talk to each other enough, which is pixel-based method and object-based method. I mean, I read every now and then papers where people claim that one is better than the other, and I really don't want to get into this debate because I think it's quite futile as a debate, because they serve different purposes and they are both very useful. And the best thing one you could do is to use them in conjunction instead of trying to figure out which one is the best. So let's say when you work at the pixel level, you are processing and considering the image at its maximal resolution. Okay, and you also have a ton of models around. Also, when you take them from computer vision, everything that relates to image analysis often has a pixel-based solution. So you have a lot of a palette of methods to choose from. But I mean, in principle, spatial info is not inherent. Now with convolutional neural network, it is. But most of it, you have spectral ambiguities, meaning that if you look at just that one pixel and its spectrum, it can be ambiguous with a pixel of a different class that is made of the same material, for example. So you really need this context that objects can give you. So objects are basically built on the concept of spatial proximity. So it would be basically to convert this pixel image in a number of segments, each one being consistent in spectral terms, and then using the segment as if it was a pixel into a model. So it has inherent spatial info, but it's also very fast because instead of having 1 million pixels from an image to process one by one, you basically extract 50,000 objects, and then you have 50,000 points to process. The problem with objects is that the moment you have done a bad choice for your segmentation, you're basically stuck in a bad result. So imagine you have a building and a street that are segmented in the same object. Well, it becomes 1 point in your data set. So it will be impossible to classify it into 2 different classes. So the thing that you should do then is to try to segment more finely and separate the two and then have them classified differently. So, I mean, it puts a lot of pressure on the quality of the segmentation, which means that you have a lot of feature engineering to do at that level, which could be, you know, the number of parameters you use on your segmentation model and so on and so forth. And then you still have to use a classifier, and it can be the very same classifier that the same, I don't know, the random forest that you use at the pixel level. Okay, so we thought, okay, why not try to make these two words communicate and run actually a model that can leverage the advantages of the pixel and the object and try to remove the disadvantages of the two words. So we acknowledge that we have two lattices, and when I say lattices, I mean spatial support. So on the left, the lattice is a grid, the pixels. On the right, the lattice is a number of objects. So you see here, every color corresponds to an object. So this is an object, this is an object, and so on and so forth. We know how to train two models, one per type of lattice. The thing that I want to do is to encode local priors, so proximity prior in each lattice separately, and a hierarchy priors, because I would like the two predictions to be consistent between each other, meaning that all the pixels that correspond to an object at the other scale, I would like them to be consistent with the prediction of the object, or to flip the prediction for the object to another class. And everything, I want everything to be in the same energy minimization framework, which looks like this. Big formula, don't be scared, it's fine. Basically, it looks a little bit like before. You remember we have this probability part at the pixel or object level. So we have two classifiers. You see, we have this S is this S sign here is the support, the lattice you're using. It can be pixel or it can be regions. And then you have all the pixels or the region in your support. So the left part here is exactly the same classifier as before. And then you have two more terms. You remember the V term I was telling you before? Here it is, it's back. And the one in green here is a hierarchy prior, and the red one here, it's a proximity prior. And everything is in the same formula, so we will compute the energy of the map and try to minimize it so that it respects the single pixel and region classification, the hierarchy, and the proximity priors. So let's look at the terms one by one. First, we have said the classifiers. So we have one at pixel level that we see here, and one at the region level. So you see, you have much less salt and pepper noise here on the right, but at the same time, the borders are very rough. So, I mean, you're tributary of the quality of the segmentation on the right, and on the left, you're tributary of the fact that all your pixels are independent. So basically, you have a lot of these effects, you know, strange class structure at the borders of objects and so on. But still, we learn this classifier, which means that, you know, we maximize the probability at each pixel and each region to be the best, which, you know, these are the most probable classes in 2 words. And you get, for each class, this probability map. Now you have the one for the buildings here. So everywhere where it is white is high probability. Everywhere where it is black is low probability. So we have buildings, we have roads. So you see all of a sudden the road gets very shiny because it's where it's giving a lot of probability. And also at the object level, you have similar structures. Sometimes we have it's not perfect, but you know, it gives you a direction and that leads you to a map that is likable. Same for the trees, you have them here. So, you know, you have a high probabilities here where it's a kind of a forest, and it seems to work okay. Now, but this is not enough because we weren't happy neither with the map of the pixel or with the map at the region level. So let's put some prior knowledge. So the first one I promised you is the region pixel consistency map. And this guy here is basically a prior that will tell you that the prediction of a pixel inside a region should be the same as the prediction of the region itself. I mean, we don't force it, but you know, every time this is different, this term goes up by 1, which means that every time this is observed, the solution seems a little bit less nice. And it forces the model to flip predictions to basically confirm this prior knowledge. Okay, so I mean, the ideal situation will be that all the pixels inside the region are trees while the region is trees. It can accept that one or two are of another class, but on the majority, it will always try to push for the labels to flip to be consistent. And so we use exactly the same idea as before. So we have the same term, that is 1 minus a function that is 0 if the labels are different, and 1 if the labels are the same. So basically, it likes this situation, trees on trees, and it doesn't like the situation building in the middle of the forest, even though it can happen. And this is why this whole random field framework is not rigid. It's all based on probabilities. So you will have these three terms, you know, the single pixel one, the hierarchy one, and the spatial proximity one, which is the one we saw before, fighting with each other to get to the minimum possible value. And I mean, if it was for this guy alone, we will have the maps we saw at the beginning. If it was for this guy alone, we will have all the time, all the pixels in a segment being the same as the segment. And if it was for this guy alone, we will have always consistency between neighbors and a map that becomes very smooth. But none of these three guys is alone, and they have to cooperate to lead to the most probable map. All right? Good. And oh, sorry, I forgot to explain you this red term. I got a bit carried away, but I mean, it's the same I showed you before. So you want for each pixel to be consistent with the direct neighbors. So you don't look at the regions anymore, you just look at the pixel lattice. And at the region level, you do the same. You want this region to be as consistent as possible as the regions nearby. And how we compute that? Well, we compute that in a very similar way as the one I showed you before. So you remember, it's 1 minus a function that is very small if you want to penalize and very large if you don't want to penalize. So you still have this 0-1 concept here that we had before that make you like consistency and dislike inconsistencies. But since, especially at the region level, you don't want this to happen all the time, we multiply it by a factor that depends on how these two nearby regions or nearby pixel have similar spectral values. So the more spectrally similar they are, the more you will trust this personalization, because your kernel function will be close to 1. The more the two regions look very dissimilar, imagine one region is the border of a building and the other is a tree. They have very different colors. So their similarity, their kernel will be very small, which will erase the penalization that is here. And so the model will decide not to flip the labels. And we use here a kernel function, a Gaussian function that basically gives you a value of 1 if you compare a pixel with itself, or if you compare me with myself. And it goes, gives you a decreasing value the more two things are different. Like in the example here with Potato Man, the kernel value will be very high because they look very similar. And the case on the right here of the actor who dubbed Sullivan in Monster and Sea, well, they're not exactly super similar, so their similarity will be smaller. Okay, so you have here a term that basically will try to flip labels if the classes are different, but only if the two objects look similar in the image itself. So let me show you how this works. And so as before, I first quickly show you the data we used. And so we used the famous, a bit famous Zurich Summer dataset from Michele Volpi. And it's basically a collection of 20 image chips from QuickBird taken in 2002. So I mean, it's not very recent images, but I mean the data are still very valid. And we have 4 bands, RGB and near infrared, and the whole thing is annotated. So these are the 20 images. You see them here. So they show you different parts of the city of Zurich, and every single one has been annotated by Michele himself, and into a number of classes that can be buildings, water, soil, railway, and so on. Everything you see in white here is background, so it's non-annotated pixel, just that you know. And so we use this data set, and in order to make sure that we are doing things properly, we separate training and test data. I know Ronnie Hensch will be very happy that I say that. I don't know if he's listening, but he's always very fond on hammering the separation between training and test, which I think is very, very important when you evaluate your models. Otherwise, you end up always overestimating your statistics, especially when you work with deep learning models. So we have on one hand 15 images we use for training, and then on the other hand 5 more images of different places of the city where we will test it. Okay, so remember, we have 2 lattices, pixels and regions. And so for the pixel size, we have 15 images. We train a small convolutional neural network to predict these classes. On the region side, I used one of these super pixelization algorithms from image processing, the Feltenswald algorithm, that at the end of the day gives you a tessellation like this one. So each color here corresponds to a different region. So from 1.5 million pixels, we reduce to 34,000 regions. And on those regions, we train a random forest classifier that as inputs takes red, green, blue infrared bands, NDVI, the water index and the YI, and then some statistics for each one of those. So the minimum, the maximum, the mean, and the standard deviation. So that gives us 24 features for every single region. So when I say minimum, maximum, mean, and standard deviation, I mean for all the pixels within the region. So that will it will give you one descriptor. I mean, you could do bag of visual words. You could be creative here. Okay, so here are the results, and so it was like the second set of experiment in the paper. So in the first experiment, we had random forest for pixel and random forest for regions. And there we observed massive improvements. When we go CNN for pixels and CNN for region as well. So yeah, it wasn't a random forest before, sorry. And we see actually an improvement that is more significant. So it's a more or less 3% improvement on the average accuracy and 4.5% on the overall. While for the CNN, it seems to have a quite minimal improvement on the pixel map. Oh, okay, I mean, this is kind of expected because the CNN is already including a lot of spatial information by design, which makes that the original map that you will see in a second is already pretty smooth. So the different improvements we obtain are more of the level of the consistency of single objects, which are way more visible at the regional level. So we see them here. And you have the region map, so those for which there is a 4.5% improvement. And I mean, you can appreciate, for example, how the river gets better recovered, because it basically takes this map, it starts to flip different labels along the river edge, because it's starting to look for consistency between neighboring regions, and also it tries to make consistencies together with the pixel map. So it allows us to increase this type of consistency in the maps at basically no cost, because the CNNs, you have them already, and you're basically improving them by comparing the output maps at the 2 level and at different spatial components. So I mean, I think this is the take-home message for the random field models for pixel classification. It is the last mile. It's the last mile to improve a final bit your prediction by looking at these rules that you know from your own prior knowledge. Okay, wow, Alp, how much time do I have left? I don't have a watch.
Normally we have 15 minutes for questions, so let me check, about 20-25 minutes, something like that.
Super. Okay, so, great. So I hope you're enjoying the ride, and now we were moving to the third and last part with this last 20 minutes, and I wanted to show you a couple of things that go beyond the proximity priors, because the proximity priors are this last mile you want to have to make your maps more beautiful, more accurate, more consistent with your spatial knowledge. But I mean, there is so much more than that you can do. Okay, so I want to show you two things. So the first is how we could use the logic of MRFs to update vector footprints in OpenStreetMap. And this is a collaboration I had with some colleagues in Brazil, the group of Alexander Falcao and John Vargas, who is now a postdoc here in my team at EPFL. And afterwards, we will talk about how to vectorize directly object footprints in a vector form using this type of logic. But first things first, let's talk about how to update vector footprints in OSM with random fields. Yeah, okay, so the story is that there is quite a lot of annotations around, and I mean, way more than we think, actually. So, you know, making object detection, it's good, but I mean, there is already a lot around that we could leverage instead of trying to start from zero, and from an image we need to detect all the buildings as if there was no information in the universe available. And you see, OpenStreetMap, for example, has a spatial coverage that is quite impressive, and in particular in the northern Western countries. So let's say Europe here and Northern America. But yeah, I mean, if you go to Africa or you know, some parts of Asia, you see that the number of footprints decreases drastically. It doesn't mean that there is nothing. There are things, but you know, not as much as you will hope, and also not often always of the quality you would like them to have. Because, you know, in urban areas, annotations are super good. So I mean, look at these guys here. This is the image. This is what you find in OpenStreetMap. It's done. So I mean, it's a very nice source of information that you can use then to learn other wonderful things. And so for urban areas, we were fine. But when we go to rural areas, especially in poor countries, sometimes it's not so present. You know, sometimes you have absolutely nothing, and sometimes you have, you know, things that are incorrect or incomplete. And this is actually what we have tackled with the studies: how to leverage what is existing and how to decide when we have something we want to do. So the first problem was that the location of the buildings annotation, when they are there, are often inaccurate. And this has several reasons. I mean, it could be the fact that when they have been annotated, there was another aerial image behind, and then with some, you know, registration problems, it has been inaccurate. Errors in digitalization, I mean, you name it. There is a number of factors that could make that your annotation are correct. They're just, you know, poorly located in space. Sometimes some annotations that are existing are not in your image, and this can be, you know, there is a number of reasons. Maybe they've you know, destroyed that building to cultivate something, and so the annotation should not be there anymore, but they are still there. And the third thing would be that, you know, maybe someone has built something in between the moment of annotation and the new image has been acquired. So you basically need to detect new buildings. So in this case, it's like the traditional object detection story comes more in here. So there are these three problems, and we try to tackle the three of them. Okay, so the first, I mean, let's just go back to the first, was the fact that we have annotations that are poorly registered to the image. So it's a registration problem. And we thought of doing it like that. So we basically took the aerial imagery, as we could get it from, you know, public sources. In this case, it was Bing Maps. And we learned a convolutional neural network segmenting buildings. Okay, so we made a small ground truth, and then we learned a CNN that could have a probability map predicting where the buildings in the image should be. So it's a CNN that looks very much like the one I presented you before. You know, you learn some features, then you upsample them, and with the upsampled version, you learn the MLP. It's actually exactly the same. It's an hypercolumn. And when you have now the original OSM annotation and the probability map, you can now start playing and trying to match them. And this matching, if you think about it, could be represented as a vector of displacement. So in this case, these are these two red arrows that will tell you, take these annotations and move them by X meters to the right. Okay. So how can we find these arrows? And here is where the prior knowledge story comes in. So we have an energy function that looks very much like the one we discussed before. So we have one part that it's specific to the single annotation. So in this case, we take the location of a current annotation and we look at all possible displacement vectors. Imagine that you have all the vectors turning around the annotation, and we want to choose which one is the most promising by looking at the correlation between our probability map and which pixels will be covered after displacement. So it's a kind of a classifier that will basically classify among the 9, 10, 20 possible displacement arrows, which one is the most likely. But we also have another prior knowledge is that usually, I mean, often when people digitize these buildings, they make them in a single session. So it means that very often, many buildings need to be displaced by the same displacement. Okay, so there is a kind of consistency that can be looked for in this specific problem. And we basically use the same idea as before, but between displacement vectors. So we look at the direction of each vector, of each arrow, and we penalize differences in angle for nearby vectors. Okay, so what we are encoding is the prior that all the arrows in a local neighborhood should point in the same direction. Okay, and this is really a random field optimization like the ones we have discussed before. Then from problem 2, the fact that some annotations have maybe disappeared in between. Well, after alignment, we look at the values of the probability below every single footprint, and if the probability of building is very small, we remove the annotation. So that's very, very manual, and it happens afterwards, after the annotation, but it allows us to basically remove buildings that would have been disappeared in between two epochs. And then the third one, that would be the one of adding new buildings. It's basically another model that tries to place building candidates on the current map. So it's basically a model that uses the image and the building probability and has a number of basic shapes of different scales and orientations, and basically tries to put them on areas of high probability that do not have an annotation on top, and then turn them and try to, again, find an optimum. And if this optimum is found, that basic shape will be added to the image. And this is learned end to end. So, but I think, you know, the most interesting part is actually looking at how it works. And so we took parts of Tanzania as a case study, and we took 23 square kilometers of linked imagery. So it's 30 centimeter resolution. So each point here actually corresponds to multiple remote sensing images. But so we use all these regions in red to train our model, and we kept one geographically separated region to test. All right, and you know, had roughly 3,000 OSM footprints to learn from, and in testing, in the test set, there were 1,094 footprints that we verified to make sure that if we added a footprint, it should be added in the right place. And the whole thing seems to work pretty well. So if you have this type of image here, and these are the original annotation, I mean, you can already see what the first problem is. They need to be displaced on the top left corner, which is what happens with the alignment that is done with the random field. So that tries to align everything in a similar direction, but every single building to go to the maximum probability area of the CNN map. Then in the second step, this guy here, because there is no building below it, and the probability map will show a very low value. And finally, the CNN that places objects will decide to place two circular objects here, because there are two peaks of the probability map there that do not have a current building footprint available. So you see, this is a way to like fully automatically try to update these OpenStreetMaps, but with an object flavor. So we're not classifying the image into pixels and then try to segment it afterwards. We're really working on the vector shapes and moving them around. And when we add something, we add something that can be directly exported as a vector shape. And also in terms of performance, it works pretty well. So we compare to a semantic segmentation network that would segment the image and then extract some region of a predefined size that you would like to have. And you know, we're doing pretty okay, like a little bit better. It's not it's a significant improvement. Yes, no, I mean, you decide, but the story is, for me, the real advantage here is that we have like vectorial objects that we can then immediately use in GIS applications. One thing that I noticed is that it's mostly the recall that increases when you remove then add, which is actually makes sense because you add new objects. So it means that you are more able to recover all the buildings that are there. But I mean, if you apply the same logic to the semantic segmentation model, so this one on the top, if we were also using the remove then add strategy, I mean, it will be very good at recall, but then precision will be lower. And I mean, I've been trying to understand why. And I mean, the answer was basically to be found by looking at the maps, is that, and it is not a problem of the specific model we have been used as semantic segmentation. It's just the fact that when you do semantic segmentation, sometimes you overclassify the buildings because it's a binary classification problem. And when you overclassify, you're sure that the object you're looking for is contained, so recall goes up, but precision doesn't, because you are also predicting a lot of things that are not buildings. And this cannot really happen with the approach I just presented you, because we add the shapes one by one. So, I mean, we can always add a shape in a place that doesn't make sense, but this effect of like bleeding out the prediction is something that cannot happen because we are not using the semantic segmentation prediction directly. We are aligning objects to the probability map and only those objects. Oof. Okay, that was the first. I hope you're still with me. That's the last time. That's the last thing I want to show you, and it's a work I'm super excited with. I really like that because it really like it's the next step, no? So in the study I just presented you, we had existing footprints and we tried to move them around. Okay, here we try to actually draw the footprint in a vector form directly using only the image as an input and some example of vectorial footprints that you could have from OSM or from your local cadastre office. And this was a work we had in collaboration with Raquel Urtasun in Toronto, and yes, it's let's just start. I don't know what to say more. I mean, first out is Diego Marcos, who is now in Wageningen, where I used to be before. Okay, so the story here is that we want to do, we don't want to do semantic segmentation, because with semantic segmentation, we're basically classifying everything that looks like a chair into the chair class. But afterwards, we need to basically figure out which of those pixels classified like a chair belong to the same chair. And when they touch two chairs, it seems like it's a single object. So we need to post-process a lot. What we want is a semantic instance segmentation type of work. because we want every single object to be segmented individually. Even if two objects of the same class touch, they will be put into two different objects represented by a vectorial shape. And this is, this is very useful, especially if you then want to import your result into a GIS, when you want to, I don't know, measure the footprint, you want to know the solar potential, you name it. But you need to be able to access information about the single object. So we decided to revive a very old method. Very old. Back to this. A method from the 80s, let's say, which is called an active contour model. And it's still pretty much used in image processing, and it's basically a method for instance segmentation. Object segmentation, if you want, that starts with a vector shape of random size and shape, and then looks at the image and tries iteratively to get closer to the object and really segment it precisely. Okay, it's also called snake, so snake or active contour models. And basically, funnily enough, it depends on an energy function. So it depends on something very similar to what I presented you before, so the random field model. So you need to imagine every segmentation result as one energy value. So each segmentation will go down an optimization function where every time you segment better, the energy will go up a little bit. Okay, we will see after which priors are used, but the generic idea is that the most you are close to segmenting what you want, the smaller the energy. So same thing as in Markov random fields. So our aim is to get to this solution represented here, the green point. And we want to do a similar thing with our remote sensing data in order to segment the building. So the idea is that we start with a random initialization of a shape. You see it here is in orange, and every circle is one edge. Okay, a vector a vector object can be defined by nodes and edges. Sorry, node. Why did I say it? So each node is it's something that you will move, and the edges connected to the node will move with it. Okay, and at the end, what we want to achieve is that each node will end up at a corner of the building. It doesn't have to be 4 corners; it can be more. And then it will really take the shape of the building. So how does the ICM work? And look, just by looking at this formula, if you have followed so far, you will say hey, but this is the same. We have on the left a term that depends only on the data. Okay, so it's a term that will tell you if a node is in the right place, basically if it's close to an edge. Okay, so the data term for this image, for example, can look like that. You could run a Sobel detector or your favorite edge detector, and then everywhere that the value is low, so everywhere it is dark, it's somewhere where your node would like to finish. Okay, it will try to go there. And you see it's a sum over all the nodes of the shape. Okay, so every node will try to move in a place that makes sense. And then you have the prior knowledge. The first one is that you want to have a contour with a small perimeter. Okay, you want your nodes to be, well spaced, to make straight lines, because a building wall like this, unless you live in a very modern building, is very unlikely. So you want your walls to be basically very straight and avoid zigzagging. And to do that, we assess the perimeter of the thing, and the higher the perimeter, the more you are zigzagging, basically. The second is the curvature. Okay, in the original expression of the snake, since they were trying to segment objects that were roundish, they were trying to penalize corners, so having a shape that is as round as possible. So this is not perfect in our case, but we will see in a second how we can use this prior to our advantage. Okay, and the last one is called the balloon, and it's basically the prior that avoids the shape to collapse to a single point. It will try to expand as much as possible the polygon until the generic shape of the object we're trying to make, the generic size of the object we're trying to segment. And if it's too big, it will try to shrink it. Okay, and all these factors, as usual, they fight against each other in order to find the optimum. So, okay, back in the day, this was the formulation of the snake model or active contour, and still it had 1, 2, 3 parameters that were to be set manually or with some heuristics. And if you set them right, you will end up with a segmentation that is good. But if you set the curvature too strong, for example, you end up with a blob. If you send the length not strong enough, maybe you start to have your shape zigzagging. And for every single building, you have to set these parameters, so which makes the snake not super good for our purpose, which is to generate footprints for millions of buildings. I mean, you don't want to set these parameters one by one by hand every time. So, okay, we thought, let's learn the parameters with the neural networks, right? So we have an engine, the snake, that will, given an initialization, give us a segmentation. What it needs are these parameters. So let's learn them. And since we are at it, I mean, why using a Sobel filter or an edge detector? Let's just learn the data term as well, so that it becomes specific to the class you are looking at and to the object that you're looking at. And that's the story. So we have a convolutional neural network that takes the image as an input, and it will predict, follow me on that, 3 maps. The first one is the data term. So it will predict a map like that. You see, for example, in this map, it predicts low values on the shape of the building because you want your nodes to fall there. There are other edges in the image. You have the cars, for example. You don't see them here. It's because you have learned this edge map to be specific to building segmentation. So this is the interest of learning that this way. The second map you learn, it's the map of the curvature prior. So we're basically learning a map that will penalize a lot along the walls to force the walls to be straight, but will not penalize at all among corners of the building. And this is learned from the data. So you see, instead of learning a single value for the curvature, we will learn an entire map penalizing in the right places. And we will also learn a map that corresponds to the balloon term that is very low in penalization around the building because you want it to shrink, and very high inside the building because you want the shape to expand. But now maybe you're starting to think, yeah, but how do you learn that thing? You don't have any ground truth for any of this, right? I mean, I don't have a ground truth for this. I mean, I could get a ground truth for the first. If I have a ground truth of the building, I extract the boundaries, and then I have a ground truth. But what about the others? I mean, you could craft them, but the thing that we thought was, why not try to learn this map by going all through the segmentation process and instance characterization, and then back propagate through the network, involving in the middle the usage of the active contour model. Okay, because the only thing we can use as a ground truth is the actual contour of the building. Okay, so basically, we will start with a random neural network that will predict the energy terms very poorly. Okay, so imagine at the beginning, your network is predicting these 3 maps, and there will be random, like very, very, very bad. But still, they are there, and you can use them in the snake model that will give you a very, very bad segmentation. And then you will compare your very bad segmentation and the true outline, and you will start moving you will be capable to see which gradients you need to back propagate to have a better priors map at the beginning. In other words, we are basically learning the energy function that is necessary to have a good segmentation. Let me show it in the image. Maybe it's a little bit more clear. So you have your CNN that predicts your 3 maps here, and these 3 maps here will go into the ACM. They basically will define how, from the random initialization, you get to the segmentation. Okay, so if you had 3 different maps here, you will have another segmentation. Okay, So basically, we are learning the priors. We are learning them this time. We are not putting them in advance. And when you have your segmentation, you compare with the true map. At the true locations, you want to have a very small energy. And if this is not the case, well, you back propagate into the neural network. And like that, you're able then to have better maps. They will help you having a better segmentation. So remember, this is a different usage of the neural network. We're not predicting a building map in the end. The network is predicting the different ingredients of the energy function needed by the snake model. Voila. And I mean, as always, I mean, it works. It beats the baselines, of course. And we tested it on a quite large data set of the infamous Toronto City dataset. And you know, we compared against the deep watershed transform here of CVPR17. That, by the way, we were also using as initialization for our network because we had the footprints. And yeah, you know, fortunately enough, the model seems to, you know, make use of these priors and really try to expand the footprints to have walls as straight as possible, and to avoid the zigzagging that you see sometimes in the previous prediction. Of course, I mean, it's not perfect, but you know, it's a first step in the right direction. And I know that, you know, since 3 years there have been other people who took from our implementation and improved it a lot. So it's actually, I mean, I guess if you had to take something that is 2021, your result will look even better than that. Voila. So my idea today was to give you like an avalanche of information to beg you not to forget the prior knowledge that we have, and to also show you how we can encode it with the classical example, which is proximity priors. And then the last part, I also wanted to show you how to predict other things that pixel maps that could like open up for other potential applications you could have. And of course, I mean, the sky is the limit, and you can be very creative with this thing. So take-home messages. I mean, we all love deep learning and CNNs, but just remember they do not do everything. And since we are from remote sensing, we know what's going on. We know the physics of remote sensing, and this is definitely something you can, you know, use at your advantage to learn models that are, you know, small, accurate, and representing actually the physical world. And it also allows you to do very cool machine learning stuff. So it's definitely worth taking the time and the effort to have a look. Saying that, thank you very much, everyone. I hope we can have some interaction now. Let's see how it unfolds. And if you're on a beach on holidays, our Deep Learning for the Earth Science book is just out. So maybe you want to have a read. It's a lot of like very inspiring material for a summer reading. And thanks to the organizer, Alp and Gilsen and Mustafa. Thank you so much for having me, and good luck for the rest of the summer school.
Thank you, Devis, for an interesting talk on the use of prior knowledge, like proximities and random fields, and also learning the prior knowledge using deep learning. An often asked question from our participants to other lectures have been explainable AI. And I wondered if you wanted to say some words about this concept in regards to your lecture.
Sure. So I didn't talk explicitly about it today, but I mean, it's a topic that is quite close to my heart. And especially from these two guys here on the far right, Diego Marquez and Alex Levering, who are working on XAI at the moment. And yeah, I think that there is a lot to do in Earth observation with XAI, especially because I mean, we can always take these models and get to the final response and then be happy with it. But you know, when we also look at who we want to use the information we produce, I mean, this is often a person who also want to know, I mean, what does this prediction imply, or why the model predicted the way it did, and having some ways of verifying this type of predictions. And I've seen some research using like heat map type of networks that, you know, like RADCAM and these type of things. And they are interesting because they highlight which part of the inputs has been important to reach to the final decision. But in my opinion, I mean, taking the step to semantics is even more important. And I mean, in the works we have been doing recently with Diego and Alex, we're really trying to learn intermediate semantic maps of what's going on inside the network. So meaning if you're predicting the forest map, the forest cover, you want to have, you know, intermediate map of forest density, height, slopes, and things like that. So, and then with the weights that you can combine them linearly, you can basically understand if the model is predicting that this is a certain type of forest because of this or that factor. And I mean, it's very interesting to go down that line because it also allows you then to be explainable for tasks that are not very well defined. So Alex here at the far right, he had some works about how to predict beauty of landscapes from remote sensing images. And then, I mean, beauty is a very subjective concept, and it's, I mean, it's complicated to interpret why a model will give a very high score for tourist attraction to a certain place. And then to be able to basically provide information about the why. So I'm saying that this is beautiful because there is a cliff and I see ocean. And I mean, you can really go very far with that and then interface with text and provide explanations that really people can understand. I mean, for me, it's a super, super exciting topic. And yeah, I encourage everyone around to have a look into this research avenue. It's super, super, super.
How about using such prior knowledge in explainable AI? Do you think there might, I mean, this kind of information might help to improve our knowledge to understand what is going on in the black box?
In a way, there is something about it that can be encoded. At some point in this beauty project, we were trying to understand if specific layouts of images were influencing the beauty score. So like to having interaction between objects we were detecting in the image. Because, you know, if you have a tree in the middle of a construction site, or if you have a tree in the middle of a meadow with the ocean behind, I mean, your perception of beauty will be completely different. Mm-hmm. And I mean, using this type of prior of co-occurrence or co-location can be very interesting to provide information that is even more like explicit for people who will interpret the results. Mm-hmm. So that's probably an avenue to look more in that direction.
Thank you.
Thank you. We have a question from the Zoom session, a question by Mümin İmamoğlu. Thank you for a great presentation. My question is about Rotational Net. Is that somehow equal version of augmentation plus traditional CNN with lower model parameters and lower training patches? Is there any performance comparison?
Haha. So let's see if I can move back quickly. Oh, I stopped the screen sharing for some reason. I mean, I can just talk about it. So it is similar in the sense that with the big network, with augmentation, when you rotate the images, you will like teach the network to react, how to react in case of rotated inputs. The difference is that you do it by bombarding the models with examples, and you will need some extra capacity in your model to take that. Rotational Net, you learn filters, one filter, and then you make it turn. So you will learn a single filter for all the rotation parameters. So it's a way to reduce the complexity of the model that you need. Now, in the experiments we had, so it was the very first graph I had on the slides when you had the two curves descending like this. You had two pairs of curves, and everyone was a version with or without rotation augmentation. So, I mean, you can use rotation augmentation with Rotational Net, it's not a problem. It will help you gain even a little bit more percentage points because, I mean, you will cover by rotated versions of the images whatever you were not able to catch by the rotational invariance.
I do have one question. Thank you very much, Devis, for the nice presentation. So considering the random fields, so we have some parameters there. So for the local priors, the constant, we have mu, lambda, and so we have hierarchical. So I think the weight is important there. So, but you haven't mentioned about how the weights are assigned in that case. So maybe you want to elaborate.
I mean, there is not a lot to say here. I mean, models without parameters are very rare, and it's almost a trial and error there. I mean, you can have a kind of a rule of thumb. No, you can say, okay, how much do you trust your original classification, so the unary term, with respect to the priors? So how much do you want the priors to influence the original map?
So is it possible? So is it possible to include a learning stage for them, their parameters as well?
I've seen studies trying to do that. It must be possible. I've never experienced that myself, to be honest.
Thank you very much.
For example, there is a work by Michael Volpi, I think it was Jersey 15, and he was learning these weights together with the interaction potential between classes. So maybe you want to look back into that. It's the only example that comes to mind.
Okay, thank you.
Okay, maybe I can ask another quick comment or insight from you. We talked with Dr. Lefebvre about multimodal change detection with deep learning. Maybe I know you have prior studies on domain adaptation and so on. Would you like to say a few words about this topic, the multimodal processing with deep learning or domain adaptation with deep learning?
Oh
I
my
know
God.
it's a huge topic, but anyway.
What if I hope I don't contradict Sebastian? I think it's a very hot topic, and it's something that it's very necessary, because I mean we can keep benchmarking stuff, you know, and you know, making as if we could have the same sensor all the time, but I mean that's not really realistic. Sometimes you get one sensor, sometimes you get another, sometimes the sensor you get is completely unusable. I mean, assume you have a system that works on Sentinel data, Sentinel-2 data, and you are in the Netherlands, like half of the time is cloudy and you don't see anything. So you need to be able to like fill in the gaps with some radar imaging, which will have other problems that will make it unusable in other situations. So I think that like multimodal learning, it's definitely something that needs more attention. But it's difficult. I mean, it's difficult because your inputs have different dimensionality. You need to craft different networks, learn joint representations. But this is also why it's super exciting, like to try to design this function that will align data spaces or allow you to move models from one geography to the other. So I mean, I cannot recommend enough to have a look in this topic. It's a huge topic, and there are so many different entry points. So yeah, it's difficult to give a 10 seconds answer on that.
Yeah. Another question from the QA interface is, could you please explain the loss function that is used in the algorithm at page 110? I couldn't understand clearly how the vertices are selected and backpropagation is performed at vertices.
Page 110. Okay, the active contour. Okay, let me show the slides again. All right. So this one. Okay, so we have a prediction. Okay, and we will have the nodes that are located at in some parts of the map. According to the active contour model, this location on the map are those of minimum energy. Okay, but if your segmentation is not placed at the exact same right place, it means that in reality there is another position where the energy should be lower. But your current active contour model that depends on the current prior maps tell you otherwise. Because I mean the final solution here, the yellow contour is the minimum found by the active contour model that depends on these priors. But if your segmentation is bad, it will mean that your maps are wrong, and you want to know how to change them. So what you will do is that you will take your current energy map at the pixel, at the nodes locations, and you will calculate a gradient that will basically try to increase the energy at those locations and decrease the energy at the nodes location of the green shape. Okay, and these are the gradients that you will backpropagate. I hope it was a little bit clearer, but otherwise, I mean, in the CVPR paper we have all the details, but it's really like trying to push down to increase the energy at the current node locations because your model is doing badly there, and decrease it at the correct node locations. Yeah.
I think we have no further questions. So thank you, Dr. Tuia, for your lecture and presentation, for contributing to our summer school in your busy schedule.
It's always a pleasure.
Yeah.
And thank you for having me.
Thank you. So for the attendees, our summer school will continue tomorrow morning with a lecture by Ronnie Hensch from DLR Germany. The lecture is concerning deep learning for synthetic aperture radar data analysis and processing. So thank you for participating, and hope to see you tomorrow.
Thank you. Bye-bye.
Bye.
Bye.
Bye.
Bye.